Hi, welcome back. So in this video, I'm going to go through an example of how we can compute the average value of a function using an integral. So this video is all just explaining the conceptual process for why this works, and at the end we're going to get a formula for finding the average value. So there aren't any examples in this video, but I really think it's important that you understand why this works and you don't just know the formula and how to apply it, because the formula, it isn't that complicated, it's not that difficult, but it's good to know why it works in the first place. And it goes back to our understanding of using the definite integral as an area under the curve and Riemann sums. So let's jump into it. So let me look at a function here. Let's say it's some function f of x and it goes on an interval from a to b. And let's suppose that I want to find the average value of the function on this interval. So I could do my best and I could try to guess. I could be like, well, this looks like the average, I think. But we're not going to be able to do this exactly. And in lots of cases, it's nice for us to be able to find averages. So we want to be able to do it precisely if possible. So to show you how this works, I'm going to just start by thinking about if we had only individual points and we were trying to find the average of that. So you've likely found an average before when given individual points, so we're going to relate this back to that concept. So let's suppose that instead we have 5 points along this curve. So I'm just going to label them here, they're from A to B, and I'll give us some values so that we can put some numbers to it. So I'm going to have 1 through 7 here. So if we have individual points and we're trying to find an average value, what we're going to do is add up all of the outputs and then divide by how many there are. So if you're trying to find the average of 2 things, you would add them up and divide by 2. Here we're trying to find the average of 5 things, so we're going to add up their outputs and then divide by 5. So I have 7 plus 6 plus 4 plus 2 plus 3. Those are all of my outputs, and I'm going to divide that by 5. So I'm getting 22 over 5, which is 4.4. So we can imagine 4.4 here as the average given these 5 points that we have. And that makes sense to me looking at that. That doesn't look wrong, but we've only used 5 points, so we probably want something a little more accurate than this. But this is the basic concept we're going to build on, that if we add up all of these output values and then just divide by how many there are, we get the average. So let's suppose we increase the number of points to n, so some arbitrary n, which is hopefully a large number to get this more accurate. So what we would do is we would add up all of the outputs from f of x sub 1, that's our first point, to f of x sub n, that's our last point. And we would divide by n, which is the number of points we have. When we do this, I can summarize it with summation notation. So I'm looking at the sum from I equals 1 to n of f of x sub I, all divided by n. So this would be my formula if I wanted to find the average value using n points. But we really want to get more accurate than this. We'd like to have an infinite number of points since we have a continuous function and we really want to be exact. So what we can do here is actually relate this back to our concept of Riemann sums. So the summation we have here is looking eerily like a Riemann sum. What this is missing though is that delta x, that width. So these are heights, right? This height is f of x, but we don't have any widths of little rectangles. So with Riemann sums, our delta x would be the width, and we would find it by doing b minus a divided by n. That's the size of the interval divided by however many rectangles we want. And so we're going to introduce this delta x into the formula in order to relate it back to Riemann sums, which are something we know about and would give us some power with integrals. So what I'm going to do is multiply both the numerator and the denominator by delta x in order to introduce it into the equation. When I say we're going to introduce the delta x, the reason we could do this is because we're multiplying by a version of 1. We're doing the same thing to both the numerator and the denominator by multiplying by delta x over delta x. That's like multiplying by 1, which we're allowed to do. So here, once I have delta x in the numerator, this is actually just a right Riemann sum with n rectangles. So we've put in that width of each rectangle, that delta x, and so we have a Riemann sum in the numerator. And then in the denominator, I'm going to write delta x as b minus a over n. So we have r sub n, that's our right Riemann sum with n rectangles in the numerator, and then my n's are going to cancel in the denominator, so I'm just left with b minus a. and this would be my average value of my function with n points. So awesome, we like this because it's a lot simpler than having the complicated sum, and it relates back to Riemann sums, which we know things about. Specifically, we know that if we take an infinite number of rectangles in our Riemann sum, we actually get a definite integral where we're adding up an infinite number of things. So if we were to now compute the average value of our function with an infinite amount of points, what we are going to do is send the n, which is the number of points, to infinity using a limit. So we're taking the limit as n approaches infinity of r sub n over b minus a. Now the only n value is in the numerator, so we can put the limit in that numerator. And when we do this, when we have the limit as n approaches infinity of our Riemann sum, this is exactly the definite integral. This is how we defined it way back when. So the numerator here is just the integral from a to b of my function with respect to x. You can think of this like finding the area under the curve. We started with individual points, but by introducing that delta x in both the numerator and the denominator, we're getting something with an integral, which is awesome, and because it's going to give us power to use integrals. So just to make it look a little simpler, I'm going to write the b minus a on the outside. So I have 1 over b minus a times the integral from a to b of f of x dx. And this is the exact average value of my function. Pretty cool. Okay, so there you go. This is our formula for finding the average value of a function. As I mentioned before, it's not actually too complicated to do since you have your bounds, and the only thing is you need the 1 over b minus a on the outside, and otherwise you're just computing a definite integral, which at this point shouldn't be too difficult. I'll save the examples for the next 2 videos. Each of them will have one example, and you can go to those to see how this happens in practice. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.